I was asked to present together with Hagai an alternative view. So I think I can do a little bit more provocative title than in a normal talk. So I will try to make a case that mass loss in common envelope happens on a relatively long time scale, and the reason for this is that because we see it happening this way. So the work that I will be showing is done together with Brian, and he actually showed some of my slides yesterday, but also other people, including people in my group in Prague. So the motivation for this are luminous red novae, or transients associated with catastrophic binary interactions. And Brian already discussed how we can explain their light curves. You can see that the light curves have a relatively large spread in luminosities and durations, and they have the complex morphology. But the important thing, I think, is that many of these events show very distinguished behavior before the main peak. And to explain these events and to connect them with these catastrophic binary interactions, the best case, and probably the only case with solid evidence, is V1309 Scorpy. So I will talk a lot about this event. So V1309 was discovered in 2008, but relatively soon Thailander et al. Found that there is ogle data going back maybe 6 years before the outburst. It shows the object brighten slowly, then fade, and then brighten again, and then there is short period variability. So when this variability is spaced with the orbital period, what they found was that the shape of the light curve changes quite dramatically. So about 6 years before the outburst, the light curve looks like a normal contact binary, two stars touching each other. It has two humps per orbital period because the binary has mirror symmetry with respect to the binary axis. But over the next few years, the light curve gradually transformed from a double hump to a single hump curve. This means that the object that's in the center somehow lost this mirror symmetry with respect to its orbital period. While this was happening, the orbital period was also decreasing. The period change was accelerating on a time scale of a few years, and the total period change was about 2 or 3%. So on one hand, this is a lot. This is probably the highest ever recorded period change, maybe surpassed by LIGO binaries. But on the other hand, it's only 2%. So this means that the physical size of the object changed only by about 2%. So this long-term behavior means that it's very hard to reproduce what we are seeing in this event using the usual explicit fully compressible simulations. This is about 2,000 orbits or so. I think that it also implies that this evolution was controlled by processes close to the surface of the binary, because the size changed only by a few percent. And that these processes might not be adiabatic, because the cooling and diffusion timescales close to the surface can be much shorter than for the host star. The third weird feature of V1309 scope was the actual brightening. So the object brightened gradually over about 200 days, about 150 orbital periods of the binary to the maximum. This is very different from usual transients like novae and supernovae, where the brightening is very fast and associated with some kind of explosive ejection. Here, it took a relatively long time, but here we can see that there is a break in the light curve, even though that there are no data. And this implies that the evolution from sort of here onwards to this peak was dynamical. This light curve also implies that whatever happened before the main peak, this gradual brightening, was potentially very important. It brightened by about 5 magnitudes in 200 days, and then by another 4 or 5 magnitudes after that. So this is not a small correction, but relatively big event. I'm also putting bars showing 10 original orbital periods of the binary to try to make connection with these fully compressible simulations. So the idea how to explain these features that we have pursued over the past few years is that the binary that's in the center, the contact binary, has somehow expanded and started touching its outer critical surface. And as that happened, it started leaking out material out of the L2 point, which creates this garden sprinkle spiral that's coming out. This material obscures the binary in the center and eventually causes the brightening. You can see that the material that's coming out does not have the mirror symmetry with respect to the binary axis, so that is already some indication that, that we could do something interesting there. This model has an advantage that it gives very precise relation between the directly observed orbital period and the muscles rate that's coming out of the binary that we could potentially infer. And the constant of proportionality is basically the specific angular momentum of the L2 point. Eventually, the stream that's coming out will also shine, and the luminosity should be proportional to the muscles rate. But in order to do better than this little, we had to do a substantial amount of work. So the idea, in short, is that the muscles rate from L2 runs away on a time scale of 100 to thousands of days. And that explains what happened in the binary, as is nicely illustrated by Stephen Colbert in this movie. So, you know, now more about L2 muscles. So what did we do about this? We did a SPH simulation of this process, but it's different from the simulations that we've seen before. We do not simulate the binary, we replace it with 2-point masses, and we inject the particles close to the L2 point. So the savings in computational time can be then spent on things that are relevant for radiative properties, like realistic equation of state, radiative diffusion and cooling, irradiation by the central binary, etc. So we studied the gas dynamics of this process, determined luminosities, effective temperature, and tried to understand this with semi-analytic models. So what did we find? Previous investigations of L2 muscles used basically just correlation and test particles, and they found two possible outcomes depending on the mass ratio of the binary, which relates to the efficiency of tidal torques of the binary. But with hydrodynamics and radiation, there are other parameters that enter. One is the initial temperature, which is basically the surface temperature of the contact binary. And the other is efficiency of radiative cooling, which we parameterize by the ratio of diffusion to advection timescales. So we can get various unbound outflows with various opening angles. We can get excretion disk, but it only happens when the material is radiatively cooling and it can actually collapse within this. But we can also get isotropic outflow when material does not cool efficiently. It's close to the binary, and the binary deposits more energy into the subject. So my student Dominika is ready to submit a paper on L2 muscles and how it depends on the initial conditions. So she studied ballistic trajectories of particles launched with offset from L2. So these two plots show the final energy as a function of this offset. And you can see that in the close vicinity of L2, there is quite a large area where the final energy is positive for the expected range of mass ratios. So even when we launch the particles with less rotation than implied by the orbit, maybe 90 to 80%, there are still regions of positive energy for the particles. But one has to keep in mind that the Lagrange points change their position because the balance between centrifugal acceleration and gravitational acceleration changes.
Sorry, what's the hatched?
Oh, the hatched, those are areas that collide, where particles collide with the binary.
Oh, okay.
So, you know, L2, the modified L2 points.
And then they re-enter the Roche loop?
Yeah, they go out and collide with,
Understood.
With this potential. But there is also the possibility that particles or streams launched from different points collide with each other, as was nicely shown by Morgan in this paper last year. So what does this mean for V1309 scope? This plot here shows the projection of temperature in SPH over the calculation in the orbital plane. And it shows that as the stream goes out, it expands, temperature decreases, but less than you would expect because there is molecule formation. And as it goes out, it collides with itself. This spiral shock thermalizes about 5 to 10% of the kinetic energy. The kinetic energy of the outflow is determined by tidal torquing of the binary, so it's a way of converting the orbital energy into radiation. The shocks are actually radial. The particles move mostly radial from outside of this radius. So imagine we are looking at the contact binary in the center through this material. If we're looking in this direction, the stream is close, dense, and has high optical depth, and would block the light from the binary. This would correspond to one of the maxima, because we see the maximum surface area. If we look from the other direction, the stream is farther away, it has dispersed, optical depth is lower, there will be less blocking of the light. So we can run calculations of this and try to understand them with some analytic model. And this movie shows how a binary would look like with L2 mass loss that is progressively increasing in mass loss rate. And the bottom panel shows the corresponding integration of this, so the phase light curve. You can see that as M dot increases, we naturally get the transition from double hump curve to a single hump curve as the system loses this mirror symmetry with respect to the binary axis. So I think this is pretty suggestive that L2 mass loss was responsible for observed behavior. And this also allows us to do certain things. So this only works for a certain range of inclinations, like 60 to 85 degrees. And this allows us to break the degeneracy between mass ratio and inclination in light curves of contact binaries, and gives us mass ratio of this object between 0.07 and 0.10. So we can take this one step further, and we can compare the light curves that we have here with the theoretical light curves, do some sort of guide by eye, and determine the mass loss history of the binary. That's shown here. The red points are what we infer from the light curve, and the gray area is the directly observed orbital period change coupled together with the mass ratio that we get from the light curve. So the match is pretty good, but it's not perfect. And part of the reason is that we have huge uncertainties in opacity of material that is 2,000 to 3,000 Kelvin and has optical depth of 1, and we need the opacities in I band. So there's actually orders of magnitude uncertainties in this. But I think this is pretty suggestive that perhaps the L2 mass was fully responsible for the observed orbital period change, and this is only due to loss of angular momentum due to this mass loss from L2.
So I want to understand it a little better. So the gray band and the period change that you observe, and you convert that to an M dot by assuming it's
Bias. Assuming that it's
all right, and then the other one is just your phase light curve, right? So it looks okay, but it's on log scale, right? So with the order of magnitude, right?
Yeah, I was saying the red points depend on opacities,
Okay.
and we don't know the opacities. The uncertainty is probably a factor of 10.
All right.
Because it's not Rosland.
Okay.
So that's potentially complicated. So what happens next? When the mass loss rate increases enough, the binary disappears and the light increases. So we do not see the binary, but we see the spiral shock inside this outflow, and the luminosity should be proportional to m dot as a function of time. So this is only 150 orbits, and we can directly simulate this with our SPH. And we put in m dot as a function of time and reproduce this light curve that is shown here. There is one caveat, which I can discuss in more detail, which has some potential implications or relations to what's happening in the binary. But maybe the easiest explanation for what needed to happen here is this change in L2 morphology that was discovered by Morgan last year. So we can put the m dot as a function of time on the same plot that we had before, and you can see that it relatively well matches. So we have three different things that seem to show a consistent trend of increasing m dot. So this means that the binary existed as two separate entities all the way just to a final few days before the evolution became dynamical. And that also there was substantial mass loss. in order to explain all of this that happened before the main peak, we needed to lose maybe 500ths of solar mass. So now previous work by Natasha and her group showed that to explain the main peak, we need a few hundreds of solar masses of ionized hydrogen in a little type 2 plateau supernova. But this expansion that happened here did not happen in the vacuum, as was already shown by Brian. And it's kind of natural that we get free expansion in the polar direction and compression in the orbital plane, and that this mechanism or this scenario is actually relevant in other geometries like supernovae and classical novae. And we are now looking into this with hydro simulations with my postdoc. So I think this illustrates very well that L2 mass loss was happening over hundreds or thousands of orbits in V1309's orbit. There was substantial mass loss associated with this, and this could have significantly changed the structure of the binary and of the orbit before the dynamical phase ensued. But this is of course not the final word, because we still need to explain the basic thing. What determines mass loss as a function of time? What happens there? How can we access these very long timescales numerically? And how do we connect what we know now, like 1D and fully compressible simulations, with what we see in these transits? There is, of course, the question of magnetic fields. And how do we predict, or how do we connect these simulations with what we observe, given that there are aspherical shocks, dust, and molecules? So if you or somebody you know is interested, I have 3 positions to look exactly into these questions starting next year. Thanks for attention. Now Hagai.
I think it's.
Andre, there's a question. Oh, there's a question. I don't see a question.
Well, I had a question, but do we do questions or is that after our
We can do
guys,
questions
or-
afterwards, or we
Yeah.
can question and interject, yeah.
You forget about your question.
Just technically it's the same topic.
Is it again? Oh, yeah, sure. Are you gonna use the mic as well? Oh, it's there.
Okay, can you hear me?
Guess not. Not for the mic, but.
Yes.
Yes, but not the mic.
So, I was asked to talk about alternative views on common envelope evolution, and of course I was very happy and very saddened to do that, because I wouldn't like to call it alternative views, but just key physical processes in common envelope evolution. So let us begin. So, does this work? Yeah. So if you think about common envelope evolution, of course we have tons of different problems. The issue is understanding them. But if I just summarize some of them, I can talk about whether the envelope is, in many of our simulations, the envelope is only partially ejected. Most of the material is not ejected. In some other simulation, it's going much better than that. The final orbits are potentially wider than what I observed. And I'll discuss it a bit. It's actually related to what was discussed in the previous passage about the timescale for mass loss and common envelope might be different than what we expected regarding dynamical timescale. So basically, the difficulties suggest you have some missing physical elements. And what I'm going to talk about is some new models that could suggest some extra important physical aspect of them. And we can think about various different issues related to both of these problems. Some of them related, for example, in order to eject the envelope, you might need extra energy sources for the recombination. I'll discuss a bit cold luminosity or radiation. We talk about accretion energy, and maybe some extra gravitational energy you can extract. The other problem is actually how to couple your energy or momentum sources into the gas itself, the envelope, and how to actually eject it. So that's related to capacity, convection mechanism. I'll discuss dust-driven winds, and potentially jets or outflows, and issues of fallbacks. And of course, you cannot do without ripples. So one of the main issues is that AGB stars, they are single stars, know how to eject an envelope. They can eject the same masses we observe in or expect in binary common envelope evolution, and they can do it all by themselves without any companion. How do they do that? Well, turns out we can actually go back 30, 40 years, and the same ideas that we suggest now for common envelope were already discussed years ago. So one of the suggestions was recombination energy, which Natasha studied a lot, and the other possibility is dust-driven wind, which I'm going to discuss now. In the case of AGB stars, the paradigm now is that actually it's about dust-driven wind, and recombination energy was suggested not to be efficient enough in those cases. But I will not discuss, of course, this first issue here. So how does it actually work for dust-driven wind? Then you have an AGB star, okay? So it puffs up during stellar evolution, and at some point it actually can start to pulsate and store some material and actually have an even more extended envelope during its evolution. This envelope could actually become large enough, or puffy enough that its temperature, it cools down very fast. It starts to produce dust. Okay, so you have start to produce dust particles, and now these dust particles basically change your opacity. So if you can think about Eddington luminosity, effectively once you change your opacity, you can actually go beyond Eddington luminosity for this case, and you start having swirling winds. So radiation connects with the dust particles, drive them away. If it's dense enough here, the dust particles actually drive the gas, couple to the gas, and drive the gas with them, and they start to producing these very slow winds that over time, over a long time scale of about 10 to the 5 or even 10 to the 6 years, can completely eject all of the envelope. So in this mechanism, AGB stars can eject a lot of mass, but over a very long time scale. What happened in our case? Well, if it's AGB, actually if it's AGB star, as I said, they can do it by themselves, they don't even need a binary. What about red giants? Red giants are much smaller. Even if they have some oscillations, they don't actually puff up as much as to get to this critical radius where dust starts to form. So you actually cannot eject so much mass from red giants using this mechanism. So what happens when you have common envelope? So this is our simulation, very similar to all of the other simulations. This is gadget 2. By the way, all of this work is by Hilah Grants, my master's student, now going to a PhD. And what you can see immediately, of course, that this whole star, the envelope of the common envelope, puffs up and becomes very, very large. So how does it look like? If you think about kind of an irregular AGB star, has some of this size, actually when it puffs up doing this kind of oscillations, it can go to this critical radius, as I said, and form dust. If you look about the kind of a post-common envelope binary, you can see it's very big. Note that actually it's a different distances. It easily goes beyond this critical radius. So if you think about this, how it looks like an AGB star, and this would be the post-common envelope distribution of material around the star. If I look on the cumulative mass distribution in this post-common envelope case, but you can see this is the critical radius where dust start to form. In order for dust to form, you need both low enough temperatures and high enough density so you can actually grow. And you see that most of the mass is actually beyond this critical radius, so you actually have a lot of dust around here. So in principle, the luminosity from the core of the star now irradiates this dust, and exactly like an HB star, so you could actually eject material. So essentially, the common envelope transforms a red giant star into an AGB-like star, and now the same mechanism of dust-driven wind can work and operate over a long time scale. And these time scales, of course, it depends on the luminosity, right? The total momentum transferred to the envelope depends on the luminosity. Of course, the efficiency of how much of this momentum can be actually coupled to the dust or gas. But in principle, it could be comparable timescale for AGB, or likely actually a bit faster, because it's even more extended than AGB, so it's easier to actually eject the material. So it's very likely to happen on timescale of, I don't know, between 10 to the 3, 10 to the 4, but maybe even 10 to the 5 years. So very long timescale, certainly longer than typical dynamical timescale that we expect in a new power system. And so timescale, so it's very important to understand what's the timescale for mass loss in common envelope binary, and I'll discuss now how can you actually measure this timescale. This should also be related to maybe planetary nebula. In principle, as I said, the AGB stars and post-common envelope cases could be very similar and should appear very, very similar. The main difference maybe is that AGB stars should be much more spherical, while common envelope binaries should produce a much more asymmetric distribution of material. So maybe, I would suggest this, I discussed it yesterday, I think, with Ursula, maybe all the planetary nebula which show spherical configuration are just regular AGB stars, but all those which are not are actually coming from common binary evolution. And the reason they are so similar, and actually the measured mass loss in this planetary nebula, is what Ursula told me, are 10 to the minus 4 or 5, something like that. So this is not the mass loss rate you expect for dynamical ejection. We eject a few solar masses potentially over a time scale of years, even at the most hundreds of years. So this is much faster, this is much slower, and this is consistent with this kind of mechanism. And this potentially can explain these two types of planetary nebula and why they are so similar, although one of them is a common envelope, one of them is an AGB star. So how can you actually measure the timescale of common envelope evolution? So I would suggest strippers. So let's say I have a common envelope binary, but let's say I have a third very wide companion. So we also already mentioned it 2 days ago, but I'll discuss just a bit more. So if the mass loss timescale is short, much shorter than the orbital period, in principle, this third companion sees this mass ejection as almost like a kind of prompt mass loss, like a supernova. It actually gets a kick and can be disrupted if the mass loss is high enough. Okay? Either that, or it could actually change its orbit and become much more eccentric, etc. So in principle, if you have a distribution of the same major axis of wide binaries, or genitals, and then we have a distribution of wide binaries which have a post-common envelope binary primary, the difference between them should actually measure the time scale and the evolution of these mass loss. So can we do that? In principle, we can. So we can take very wide main sequence binary. What we see here is the separation. This is can get this using Gaia, and you can see the distribution of same major axis, multiple distribution of wide main sequence binaries. And then we can check what happens for various types of post-common envelope binaries, or something that experience a common envelope, like SDP stars, post-common envelope binaries, CVs. And first of all, each of them, you can immediately see that they are very different. This is just a cumulative. It's actually what it doesn't show, and show in the next slide, is you actually lose many of these binaries. So cumulative just normalized to 1, but it's not only the distribution of the major axis which changes. So, as I said, you can actually potentially become more eccentric, but it's also how many of them are actually lost from the system through these kicks. In principle, if it was just an adiabatic mass loss, what you would expect is you take the separation of main sequence wide binaries and just more or less move it to the right by a factor of 2, 3, depending on the mass initial and final mass ratio. This is certainly not the case. It's certainly not adiabatic, which is not mainly surprising. To be adiabatic, really it needs to be very long time scales. But it's not very clear what about the dynamical. If you actually do not normalize it, just but actually take the actual fraction, this is not really well measured. So I'm not sure this is the case, but it seems like at least 50% or so of the wide binaries are actually disrupted because in this case it's for SDP stars or post-common envelope binaries, and you should need to find a mass loss time scale which could be consistent with effectively transforming this into this. So in a sense, this is a measure. So this is a work in progress I'm doing with my former PhD students, Erz Michaeli and postdoc Andrei Goshev. We already showed in my paper with Erz Michaeli that in case of 2 specific systems, the most likely timescale that we found were actually about 10 to the 4 years.
Is this normalized over some volume that you are sort of
Yes, you look up
assuming
to
is complete?
yeah. So you look up to some volume that Gaia can, that we have relative
Yes.
completeness up to. Of course, we cannot see the faintest star companion,
Yeah.
but we do the same normalization both for the main sequence and for
Okay.
our post-common
Okay.
library. So irrespective of
And that's how the
that,
cumulative distribution can happen.
and there
Okay.
shouldn't be many biases regarding post-common binaries versus just main sequence
Yeah.
in this context.
Okay.
Okay, but as I said, it's work in progress, but in principle, this is a very interesting observational tool that we have not used until now to actually measure the time scale. And as I said, in one case, we'll actually look on two specific systems where we know the masses was very large, so we can certainly know that most of the cases should be actually disrupted. We get that, and they're not disrupted because we see the third companion at very large separation of thousands of AU, even more. It's most consistent, let's say, with about 10 to the 4 years, but no, this is not the definite answer. It's something that we need to look on the statistics. Okay, so this is about last driven rings. I will discuss some mechanisms I'm not working on, but at least mention them. It's important we discuss them here. So we could actually have accretion energy, right? Additional energy that you can get from accretion material on, for example, the inspiraling object, especially if it's a compact object, but not necessarily only in this case. So if it has non-negligible accretion, and you can couple this accretion energy into the gas, you can actually transfer energy and eject it either through some jets or disk outflows. So I think Noam Soker is the main, one of the main proponents of this idea. And so he asked me to show one of his movies. What they have here is binary common railroad, but you cannot see, but you actually produce jets. You see it in a second when they move to a different view of this. And now you can see kind of from above, and you can see these jets going on. And this is, it's always on the edge of the binary, of the giant star, and kind of takes off the envelope kind of one shell after another. We call this grazing evolution. So whether this works, it depends really on the microphysics of the accretion itself, which are not very well understood, of course. And the other thing is, of course, that you need to be self-consistent. This movie is not self-consistent in the sense that it shows specific accretion, which is constant in time, okay, and some specific conditions for the jet that they eject, etc. But in principle, you need to be self-consistent. So amount of accretion is related to amount of energy that you release. As long as you don't do this, it's not self-consistent. It might, you should actually have this regulating mechanism and feedbacks. It might not work. It's not very clear that you can actually accrete enough material to get enough energy from that. So there are many issues, but certainly it's an interesting physical aspect that we need to think about. It's not trivial, but it's not important. It's very likely that in some cases it could have some important aspect. At least even just observation, if it's not important for the common network itself, it might be very important, very interesting to see observation, and we should actually certainly look for that and think about it. Well, I told you it's not about just boundaries. We should think about triple common envelope. I know we have enough trouble with binary common envelope, but if you actually want to understand triple population synthesis evolution, we need to also understand the triple common envelope that can happen, especially given that these four massive stars, most of them actually reside in triples or higher multiplicity. So certainly for massive stars, this is critical. Less important for Roma stars, but still even there, a very non-negligible fraction of all stars, even normal stars reside in triples. So with my student Hila, we actually start to do this triple common envelope. So again, we have a each star, so this is something different from most of you have shown until now. Now you can actually see the binary. Of course, the phase space of configuration is much, much larger because now we have all this information, the different binaries in a binary separation, etc. The interesting thing is that, okay, you start having this trailing arm, but now we have this energy coming from the gravitational energy of the binary itself.
But Guy, what's the mass?
In this case, I think it was, what was it? I think it was 2 half and a half, I think. If I remember correctly, I need to check this. It's actually the same, exactly the same mass ratios as I showed you in the first simulation, but now the companion was replaced by these 2 stars. Each one of them have half the mass of the original. So now you can see that you actually eject in this arm, you actually have this propeller thing and you eject. As it goes around, it has extra energy. And now you have this complication in evolution because you actually disrupted the binary and it will actually become very, very complex and involves both the dynamics and hydrodynamics. In order to actually study the dynamics accurately, we coupled kind of more accurate n-body case with the hydrodynamic. Yeah.
So, right, if you have a triple system, it's typically only stable if there's a hierarchy. And it looks like in these mergers, probably a significant fraction you're gonna have a third body ejected.
Yes.
Is it possible to look like in guide data, see like remnants of mergers, and then see if there's some star that has a trajectory that might have been ejected from it to test this hypothesis?
Yes, so I would suggest actually to look on planetary nebula which have very unique structure, because it would be different even the post-continental binary planetary nebula because of this different ejection, and especially for them, maybe look for a search companion. Because, but in principle, it is possible to do this guy, as long as the timescale is short enough that it didn't get too far. Okay. This is a different configuration. It's just fun to show the movies. So this is different configuration with different distribution, and actually the whole evolution looks very differently. And well, not surprisingly, triple evolution could be highly chaotic. So certainly the last stages could be highly complex. So initially it looks not that different. It takes a bit longer, but later on as it goes, you can start to see how it becomes more eccentric. It starts with a circular orbit, this binary, and it becomes more eccentric. You can see it from the its movement, the time scale of the pericenter versus the apocenter. And at some point, of course, excited eccentricity become more separated, and then it will actually become disruptive even earlier than in the previous case. Again, you can see this trailing arm around this orbit. You can start extracting some energy from the binary itself at the same time, and then it starts going inspiring into the envelope. As I said, this case is actually much longer. It takes a longer time for this to happen, but now you start already getting to the disruption regime. Second, I think.
A guy?
Yes.
What is the initial ratio of the periods that you do?
So you can see, so actually we tried different cases, but you could actually just see from the separation. So this red giant is about 80 solar radii, I think, and it's a bit above that. I think it's 1 in 10, if I remember correctly, or something. So it started to settle, and you can see the final case where it's rejected and we're going away. So this is just actually for your question about Gaia. Okay?
It's coming back in the end.
It's coming back. Okay, just finish with maybe just let me finish the last question. So just finish with another observational aspect in the area of gravitational waves. So I think about the futures, 40, 50 years from now, not LIGO, but LISA or DECIGO. So what I show here is actually, if you look on the common envelope, right, evolution, this is very simplified. It's actually not full hydroid, but a very simplified kind of gas dynamical friction evolution. But it's a bit different, but it actually illustrates with actually a different kind of orbit, depending on the mass, whether it's a white dwarf, a neutron star, whatever that goes into the envelope. You can see this in spiral. And as I said, as I told you before, this in spiral changes the acceleration of the binary, not through gravitational waves, but it can actually get to the gravitational wave regime where you can actually detect it, and then you can see this acceleration through a very unique kind of gravitational wave signature, which is actually different, and you can actually calculate the strains, etc. And you should actually have a very different evolution than what you expect through gravitational waves, right? Because the dissipation is not through gravitational wave, but through this gas drag, or gas dynamic friction, but the emission gravitational wave is coming from that. And if you actually want to look on how it looks on the strain analysis, you can see it, of course, for different kind of binaries, but you can actually get it with a very large signal-to-noise ratios. In some cases, even in the LISA band. Of course, the rate of these might be very small. So you want to get
what distance?
What?
Where?
Sorry. This is for if I remember correctly, this is for 10 kiloparsecs. So this is a galactic. Okay. So if you want to rescale it, of course, to extragalactic, then of course it goes down like the mass. And this is why I say that in LISA you might not be able to do anything extragalactic. With DECIGO you should be able to do extragalactic, and then the rate become actually sensible in the sense that you might actually even detect this. But actually these are lower limits, because what we had here is this just simple gas dynamical friction approach. The next step is actually taking the full evolution from our hydrogen common envelope. What typically happens is that it's actually the inspire is a bit slower than in this case. And the slower inspire actually gives you a better signal, and it's actually going to increase. Because what you see here, these are white dwarf inspires without any gas, that's gravitational wave. So in principle, this is the upper limit that you can get. But what we should expect is something actually in the middle between what we show here and something which goes over there. But anyway, it's interesting. It's not for now, for the future. I think it's an interesting aspect. And I basically finish with that. So dust-driven reads, I think, are critical whatever mechanism you want to do, you know, puff up the envelope. You should form dust. Actually, I don't need to say that you should form dust because in all of these dusty transient, we see that dust is forming. So we know dust is there, even from observations. So dust forms. You should eject winds, irrespective of the way you do it. What I suggest it actually could be a main mechanism for ejecting the envelope. Even in the cases where other mechanisms don't work, it should always be there because the core luminosity of the remnant is pretty high. It could do it over a time scale of 10 to the 4 years or so. And I did mention one thing, which is fallback material. I think it's also important. We didn't discuss it enough here. In principle, if you eject material and it falls back, you can actually extract a bit more energy or angular momentum from that. I think it's something we should discuss more. And for this, we need to do actually very long simulations. So I think that much to that, but I think it's also an interesting aspect. And finally, triples are interesting and important. First of all, dust is observational, using them for observation constraints, very different from other type of observation constraints that we have now. We can actually use them, and very preliminary results suggest that it could actually be long time scale, but hopefully I have a more definitive answer about that in the coming months or two, and then when we submit the paper. Triple common variable is important and interesting. We should go at some point beyond binaries, because triple are important, as I said, mostly for massive scale, but overall. And we should remember gravitational waves as becoming part of our arsenal for studying any physical process, including common envelope evolution. Thank you.
You should run the discussion with that.
Okay, you also mentioned the problem that the binaries remain too wide in the end. So how can you solve it?
So this can potentially be done using maybe this material fallback, the same matter I mentioned. So you can extract extra angular momentum from this after it fallback. So stars lose energy, it cools down, and shocks a bit, you can fall back, you can extract some potential momentum. There was some discussion of this resonant interaction that can actually extract angular momentum from the orbits. That's also related to this production of eccentricities for larger separation orbits. So these are some of the possible ways. For myself, I still want to better understand the observation, whether how difficult is our problem with small separations. I think it's something still to be looked on, and whether how really critical is problem and for which kind of binaries. Because if you look on very specific binaries, we certainly haven't looked on massive binaries in this context, etc. So it's a potential problem, and some of these aspects, I think that these recommendation, Natasha, can get them a bit deeper. I think in this file. So there are several possible solutions. I don't have the answer. The dust-driven winds certainly do not help in that context. Okay, so dust-driven winds certainly can easily help, and so I think can easily solve any ejection problem. I think they can easily do it on long time scales, but they can easily do it. They cannot help you much with the deeper installs.
Well, to comment on the first part, because first, I don't think it's an alternative part. I think it's actually part of what we have already developed. I'm talking about people like Natasha and myself. And specifically, I don't think you have seen our paper, the paper of my student Matthew Clayton on that, because the whole paper is just about that. And we show that after this dynamical plunge-in phase, what we call the slow spiral-in phase, the common envelope system does resemble an HEP star. And we show that you get these episodic mass ejections, exactly like you described, except that the role of dust is a little bit different. But we eject the envelopes on a time scale of 1,000 years, so that's exactly what you're saying.
It's a fully self-consistent calculation with
Yeah.
estimates.
I certainly know the paper. I looked at it.
And that's exactly the whole paper. The whole 20 pages are just about that.
I wouldn't say this. Probably I've been our referee on this paper, right? And we discussed, we can actually show you exactly the number of times dust is actually mentioned there, and the importance of dust is not there. The whole recommendation issue and some coming up and down, that's
not
fast.
an issue.
At least, if I understood correctly the paper, the actual dust, the coupling and all of this dust-driven wind is not a main part, at least not in the paper I wrote.
But
No, the dust forms later, sure.
Yeah, but that's an interesting question, I think, and to talk, because I think in your model, maybe dust is not a fundamental ingredient. If that's the case,
It does form and it does accelerate ultimately.
Okay, but
it's not the
But this is my issue. I'm talking dust.
correct. No, but let me finish. If that's not the basic ejection mechanism, it's very important because you're making a claim that dust would be a key to help the removal. So that will mean that this process has a strong metallicity dependence, which is something interesting and potentially testable. So I think that it's nice that there's two ideas on the same line, but maybe using different mechanisms, and maybe studying a little bit more the role of dust is a good idea.
Well, I would say it this way. So dust was taken into account in the calculations. The point was is that the instability which is developing in case when this star is moving into HB, and that HB is more expanded and cooler than a normal HB. So that instability starts to do the mass ejection faster than normal HB winds.
So I said, I don't think it's 10 to the 5 even earlier. But, as I said, this will be relevant even if you don't have important accumulation energy. So maybe for massive star or the other one. As I said, dust is important, could couple to other mechanism. It's not a replacing of any other mechanism. As I'm saying, it's important physical aspect that need to be incorporated in any kind of.
It's true. What I would say though is that something you haven't mentioned much when you're. It's not just that you're turning a red giant in AGB. What you're doing, you're changing the luminosity to mass ratio. That's the important point. That's what drives. That's what drives the instability of the envelope. Then once you get there, sure, you can put mass loss, you get lower temperature, you get dust, and then you can add radiation pressure on dust. That can help you further. I think it's true that to get there, you need to change L around, otherwise you never get there.
So one thing to also take into account when you have these mechanisms that act over a longer time scale is that you also have part of the envelope that while things are being ejected by instabilities or dust is going to fall back dynamically and then thermally, and that is going to interplay with the orbit.
Yeah, that's what I had as a shell triggered ejection with the envelope fallback.
But the orbit
The
could both,
fallback was triggering another ejection, yes.
and the orbit could both become
It did not
smaller
affect-
and or larger depending on the
It
angular
didn't affect the
momentum.
orbit, it's just the envelope itself. It's instability envelope itself which was triggered by fallback.
But the inner parts will also play a role, and
Well,
they are
it's
bound.
so much decoupled. It doesn't reach the inner
But
part.
while you're ejecting the envelope, you can't afford to merge every single system. That's what I'm saying, right? Because you got time, and some of the envelope's going to fall in inside. The inside part is not unbound at all. It's just lifted just after the dynamical in spiral. The envelope's lifted kind of out of the way, and in the meantime, it's going to fall onto the orbit, and the orbit's going to change.
It has so much angular momentum. I mean, it's not very much when
Right,
you think
that-
about this at this distance, but it cannot fall back all the way down without losing that angular momentum. It takes, and it's much, much longer than your time scale for the fallback. So as a result, you cannot have a full fallback.
Yes, it's not just dynamic or ballistic.
I have a question because I really don't understand what's the difference between the grazing common envelope and just a mass loss, honestly speaking. I mean, when you rotate around, I mean, for me, it's a mass loss. Why do you need to call it as a grazing common envelope? I mean, any invention of a new term just confuses people, right?
This is not my main paper or whatever. I just wanted to mention this issue. So I think the important thing was that putting this grazing in the name. Maybe that if you are fully enveloped, right, it might be not it might not be very very well efficient in actually producing this jet. If it's the outside, you can get this accretion, and you
It's
don't.
just normal mass transfer.
No, it's
So
not.
can I-
It's much different. The way the jet, the sculpting of the outer envelope by the jet, you're literally ripping away the outer parts of the envelope by the jet.
Can I intervene? So Noam did this grazing envelope evolution, which is not self-consistent in that there's no self-gravity, right? So I made an honest man out of him and invited a student to come and do the same, but with the ENSO common envelope simulation. So Sagiv came and we did exactly what we've always done with a jet. So it's not grazing anymore. It's smashing into the pasture, right? It's going in. Normally, and so the two big differences are that the final separations are wider, and the other one that you have about 30% envelope unbinding, so a bit more. So if the jet were to happen, and that's a big if, because of course, as Morgan showed, maybe the disks are not so happy inside the common envelope, but if the jet happened that way, you eject a bit more, you're left a bit wider, but ultimately, maybe it helps. It's a normal common envelope with some gizmo on top.
I disagree with that. I mean, I think that, I mean, because that was the first cut at that simulation, and there's a lot more to be done there. And you'd expect, you're going to get, it's going to be hard to not, what we understand about jets and disks is that during, anything that's happening beforehand, before you get to common envelope, you probably already have a disk. That's going to be pretty hard not to avoid. If you have a disk, you're going to get a jet. And so you're coming into into common envelope already driving material out at what could be significant mass loss rates, right? You're going to get 1/10 of the accretion rate into the jet, right? So once that hits the outer layers of the common envelope, you're going to do quite a bit of damage. Now, whether or not, I mean, I'm not sure it's going to actually fundamentally change your orbital separations, but it's going to change your star quite a bit. And at some point it may quench. I mean, this is the question that, you know, we've been asking. But you probably are going to be able to get quite a ways down before you quench. So I think, you know, we should expect jets out of these systems because we know that every time you get accretion happening, pretty much you get a jet in these kinds of things. So we should expect a jet, and the jet can do quite a bit of damage.
Yeah, I mean, but the jet, it depends on what you assume about the opening angle, and of course, if you enforce that the spiraling will take a long time, then your jet may provide the damage, but if it's just an orbital period, no.
It's right, Leon spiral is pretty regular, but of course.
It's probably likely that the jet is more influential in the Roche-Low phase, where it's not going to be hitting the envelope, just because you have longer time to blow up.
Right, well, this is the question of the time scale for.
Sorry, I have a question. So like, this is a question for the slow injection people, actually. We had a bunch of discussions about the right, what's the right measure of when stuff gets blown off the star, whether it be just purely mechanical or basically thermal energy, right? And the argument against thermal energy was that like puffs up, radiates away, cools down, and now you're toast. Right? But then the slow injection scenario, you still have the same problem, right? Because you have to keep stuff at a fairly large separation for a long period of time. And the only way to do that, right, is basically you have to include the thermal energy in that case. So how do you avoid cooling in that scenario?
But the cooling is radiative cooling at the surface. That's of course all included in that.
Right, okay.
And in fact, when you get these unstable pulsations, and
Yeah.
they're unstable, but they reach a certain amplitude, namely when the cooling dominates and takes out the energy. But then they grow, and once every 10 years or so, the pulsation becomes a shock, which is partially driven by recombination, and that provides episodic ejection events.
I see.
And that's
So the
all
thermal-
calculated
so the thermal-
completely self-consistent.
So the thermal energy is not entirely radiated away in
Well,
a
it's just-
simplistic picture that we've had basically in this
Well,
dynamic.
you have a surface, and the surface radiates away.
I think the
whatever
question,
velocity it is.
the question is how much.
This is a standard
If you think about the
conversion.
total energy budget, right?
Yeah.
How much is coming out as integrated luminosity versus
How much coming out
integrated
as
mass
mechanical?
loss, right? I mean,
Yes.
there's a ratio there.
Right.
And that's, related fundamentally to the alpha in this, in
Right.
the situation,
But-
right?
but
all the
sound-
luminosity produced in the slow spiral-in is radiated away at the surface.
But some of it
Except
has
that
to
some
go
of it is
Some has to
going
go
into
into
yeah.
kinetic energy.
Right,
otherwise,
some of
right?
it.
in that energy,
And
right?
that's what I'm wondering is what is
So
the
we have-
ratio?
so
So the alpha would be very small if you wanted to do that.
You want-
Okay,
okay.
so that's
It's a very inefficient process in that regard.
So the answer is that a fraction of thermal energy is ultimately converted to kinetic energy via these pulsations,
And then that this thermal energy is restored again by the radiation.
by the radiation coming in. Okay, so roughly what's that fraction? Your model?
10%.
10%.
That's our alpha. Yeah, about 10%. A bit less than 10%.
Yeah.
5 to 10%.
5%.
It's actually, in terms of, the alpha is completely meaningless at that point.
Right,
But
right.
it's an inefficient process in that